Hello, this is the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And within that playlist, I'm creating little mini-series that deal with different types of experimental designs. In this little mini-series, we're doing a repeated measures, one-way fixed effects ANOVA. And I'm using R to illustrate the 6 videos that we did with this design. Now, I always like to remove all the objects before I start, and that's what that first command does. Now I searched the internet for repeated measures, one-way fixed effects ANOVA data, and I came across a website from Jason French, and he had some data on the balance. And if you search valence psychology, it'll make more sense. But the main research question is, does valence of the word affect the rate at which items are recalled? Now valence, a positive valence means, happy thoughts or, a positive experience. A negative valence means like anger and fear. It's a negative experience. And neutral, of course, is in between. And so if you search repeated measures in R, Jason A. French, then you'll come across his website. Now I'm taking the data from his website, and here it is. Now it's sorted by subject and then valence, but valence is our treatment, so we need to sort it by valence and then subject, and so that's what I do here. So it's sorted by valence and then with subject. I want each of these to be factors, so when I plot them, we get this. Now notice that the neutral valence has the least recall, and the positive valence has the most recall, and a negative valence is the middle one. And we can also plot it by subject, and the red is the neutral valence, black is negative valence, and green is positive valence. Now in part 1, there was model development, and so we created the vectors, the y vector, which is the response vector. So I just put the memory recall in it, and let's even plot that. And then we need to create the x variable. So I calculate n, which is the number of subjects, and a is the number of treatments, and then I have it automatically calculate this design matrix. So we have the first column is all ones. The next 3 deal with the 3 treatment effects, and then columns 5 through 9 deal with the subject effect. And notice it's their little identity matrix there. And that follows exactly what we did in the video. Now, we need to separate them into 3 different 3 partitions of this matrix. The one vector, x tau, which deals with the next 3 columns, and x beta deals with the next 4 variables. Okay, so that's what we did in part 1. In part 2, we dealt with perpendicular projection matrices, and so we need the mass library to calculate a generalized inverse. Now, although we didn't calculate the least squares estimate for beta, this is how you do it, and this is an estimate of the beta parameters, the mu, tau 1, tau 2, tau 3, beta 1, beta 2, 3, 4, 5. It's not unique. The perpendicular projection matrix, we calculated J, m tau, which is associated with the column space x tau, and then m beta, m, which is the perpendicular projection matrix for the whole column, or for the column space of x, the whole design. And then I is the identity matrix. And then some of the properties that we looked at in part 2 was x tau prime x tau, and it created n times the identity matrix. And then x beta prime x beta created the identity matrix times a, which is 3 in this case. More properties, we calculated the treatment mean vector, which is mu tau times y. And here I use aggregate to calculate the mean treatment means. And notice that 27.8 is here, 11.6, and 40. So I'm showing you sort of the structure of the mean, the treatment mean vector. And then we calculate the block mean vector, or in this case, subject mean vector, which is m beta y. And if we calculate the subject means, notice that it's, it's this order, 26, 24, 30, 23, 27. And it's that order, and then it repeats, and then it repeats. And so that's the structure of the block mean vector. And then the grand mean vector is just j times y, which is just the grand mean repeated, n times 8 times. Now in part 3, we looked at the column spaces of each of those components, and then we used that to calculate the structure of the perpendicular M, the perpendicular projection matrix, onto the column space of X. And one thing we noted is that M was equal to M tau plus M beta minus J. And if we run it through this all dot equal function, it compares component-wise, and notice they're all equal. We also calculated the rank of each of these matrices. So the rank of J is 1. And notice also I calculate the sum of the diagonal elements of J, which is the trace. So since they're idempotent, the rank is equal to the trace of that matrix. And so the rank of M tau is 3. The rank of M tau minus J is 2, so it's 3 minus 1. Rank of M beta minus J. Rank of M is 7. The rank of M tau plus M beta minus J should be the same, and it is. And then the air degrees of freedom is the rank of I minus M. And all this is discussed in part 3 of the video. Now notice here, if we combine J, M tau, and M beta and look at the rank, it's 7. And here, if we combine J, M tau minus J, M beta minus J, it's the same rank, because we're just orthogonalizing the column, so we're not changing the rank. Now in part 4, we've looked at partitioning the sum of squares. And so the total sum of squares is y transpose I minus jy. And if we look at so this is this next step is an AOV. So we're treating valence and subject as fixed effects. And I do that because I will look at the sum of the squares for each of those. Now this 2177 is total. So if we add the sums of squares for each of these, the valence, the subject, and the residuals, it should be 2177. So that's what this next step does, and it is. Now the treatment sum of squares is 2029, which is equal to what we get in the ANOVA table. The block sum of squares is M beta minus J, and that's 105, so it's the same. The air is, Y transpose I minus M, and it's 429.9. But notice here I use I minus M, but we could use I minus M tau minus M beta plus J, because that's the structure of M. We get the same thing. Then, so here we compare, what if we just were to use this as a completely randomized design versus a repeated measures design? So this next step, we leave out subject as a component of air and calculate it. And notice the air is 148. And if we look at this previous design, that what we're doing is we're taking that error, the residuals, and we're dividing it or splitting it into subject variance and residual variance. So these two should equal this, and that's what this next command does. It takes those sums of squares and adds them from that previous design. We do get the same thing. Now the distributional properties was part 5 in this little mini series, and here we had to show that the two quadratic forms were independent, and so this should equal 0, and it does. So I minus m times n tau minus j, and I just rounded to 2 decimals because some of these zeros is like 0.5, times 10 to the minus 17, and it really just makes it look ugly, so I just rounded it. Now the mean square treatment is sum of squares treatment divided by degrees of freedom for treatment. Mean square error, same way. The F test is the ratio of those two mean squares. And the p-value is the area in the tail from that test statistic. And if we look at the ANOVA table, we can look at this. So the mean squares are the same. There's mean square treatment. That's the same. Mean square error, 5.36, which is 5.4. The test statistic is the same, and the p-value is the same. And we're not interested in subject effect. Plus, this is treated, assuming it's a fixed constant in this design, so it's not exactly this. Correct. Now, the fitted values, m times y, or m tau plus m beta minus j times y, or just grab the fitted values from the model. And I just put them in columns side by side. And notice that they're all 100% the same. The residuals, I minus my, or just grab the residuals from the model, and notice that those are all the same. Now in part 6, we look at contrast, and here we looked at what's called treatment contrast, because we're not interested in the subject. You can't, well, plus they're random, so they're observed values of a random variable, so it doesn't make sense to create contrast from them. So we only created the treatment contrast. And so I need the LME4, which is the mixed effects model, and then EM means, which is the estimated marginal means. And actually, I just recently discovered this library. And I wish I would have used this for my one-way fixed effects ANOVA, because it's cool, it's pretty powerful. So here we create a repeated measures one-way fixed effects ANOVA. So valence is fixed effect, and then putting this in parentheses, it says this is the random effect. We're trying to predict recall. REML is the method. You can have maximum likelihood or restricted maximum likelihood. REML tends to produce more unbiased estimates. So let's run that, and let's look at the summary. Now notice it has random effects, which is just the subject and the residual. So this is the the variance associated with the subject between subject variance and the residuals that within subject variance. And these are the fixed effects and correlation between the fixed effects. So let's kind of explore this. Let's look at the ANOVA. Notice that when we run the ANOVA from the repeated measures one-way fixed effects model, and then we look at we treated subjects as a fixed effects, and then we look at that ANOVA table. Notice that the valence is the same, right? Because that's the fixed effects component of this design. Right, so that's the same. Now let's create two orthogonal contrasts, and perhaps to be more specific, I should say treatment contrast, right? Because we have three treatments: negative, neutral, and positive. And so let's create these contrasts. Now, because technically a contrast has to, it's the lambda parameter, which is a vector that times that whole beta vector. Has the mu, the taus, and the betas. And so technically this is a little shortcut to that. And then I just randomly create a second contrast that's orthogonal. And so let's look at the first contrast. Now I put it in temp contrast. I didn't need to do that, but I create a P1, which let's look at it. And so if you look at my 4 videos on contrast and one-way fixed effects ANOVA, this will make more sense. But what you do is you take the first component, see this C1, you repeat it 5 times and then divide each of those by n. 1, 2, 3, 4, 5. So each of those divided by n. So then you take 1, 2, 3, 4, 5, and divide each of those by n. So that's 1 divided by 5, which is 0.2. Then you take this component, repeat it n times, 5, and then divide each of those by 5. And so I'm creating this P1 to have that very specific form. Now, in order for this to be estimable, it has to be part of the row space. And so we take the row transpose, and that's what I call, row 1 transpose times x. And that should create the lambda vector needed in order to be estimable. And notice it does. So it's 0, 0, 1, these 3 components here, 2, 3, and 4, those deal with the taus, right? So this deals with the mu. The last 5 deal with beta 1, 2, 3, 4, and 5. And these are the tau 1, 2, 3. And so, since this is part of the row space, it is estimable. Okay. And now the sum of squares contrast for that is this. And it has a very specific form. And if you look at one-way fixed effects ANOVA's, the 4 contrast videos, then I go into great detail. So this is the sum of squares associated. So notice that the sum of squares for valence, and that's what we're splitting up, is 20, 29, and this covers most of it. So this comparison of the neutral versus the positive, it actually creates the most variance or variability. Now let's look at the second contrast. And it also has a very specific form. So it takes the 1, repeats it n times, which is 5, divides each of those by n. Now this 1/2, it repeats it 5 times, and then divides by n. So it's 1 divided by 10, which is 1/10, in the same way with this 1/2. Now let's see if our contrast or is part of the row space. So row 2 transpose times x should get us that lambda vector back. And notice that zeros and zeros, because we don't want the mu, we don't want any of the betas. And this is tau 1, tau 2, tau 3. And so we do get it back. So it is estimable. And then the sum of squares associated with it is 13. And notice that when you add these 2 contrasts, you get 20, 29, 733, which is what this is, right? That's the sum of squares treatment. And we can just calculate it. It's y transpose m tau minus j y transpose. And we should get that value back, and we do. Now, in part 6, we also looked at a theorem that says rho times m is the same as rho times m tau. And let's look at that. And notice that these 2 vectors are the same. And we get rho 1 prime back, right? So this is rho 1. They're the same values. And if we just look at the contrast, remember it's repeated, this is repeated n times, this is repeated n times, each divided by n. Now let's look at rho 2 times m and rho 2 times m tau. We get the same values, and that was part of the theorem that we looked at. There's row 2, it's the same. Our contrast was this. Now let's explore these contrasts, and this, we only got about 10 more lines here. So the two contrasts were this, two orthogonal contrasts. And so let's look at the levels of balance, so negative, neutral, and positive. And let's calculate these contrasts. So this is the estimate of the contrast, and this is the estimate of the contrast. Now, so these contrasts we said were just linear combinations of the treatment means. So let's look at the treatment means. Recall that these are the treatment means. And so this one was the second minus the third. So that's what this line does. It takes 11.6 minus 40, and we get negative 28. And then this contrast, negative 2, took the first minus the first times the average of the second 2, and we get minus 2, so it's the same. Now the sum of squares is a chi-squared, and then if we divide it by the mean squared error, then it creates a F distribution, but the numerator degrees of freedom is 1, so if we take the square root of that, we actually get a T distribution. So let's look at the square root, the sum of squares for contrast 1, divided by the mean squared error, and it's 19.3, and note that we get the same thing here, 19.3. Now, it's negative because this estimate is negative. Now let's take the square root of the second contrast, sum squared error, or the sum of squares for that second contrast divided by the mean squared error, 1.576, and that's what we get. Now we're going to calculate the p-value in the F distribution. We're not going to do the T distribution. So look at this p-value. It's really small, and here it's small. And then the p-value for the second contrast, 1536, and that's what we get here. Now, one note though, the degrees of freedom. Now remember, the sum of squares contrast has 1 degree of freedom, and then the degrees of freedom associated with mean squared error, if we look at that, it should be 8. Yep, 8. And anyway, so that's what this is. There's 8 degrees of freedom. Okay. Well, that's all I have for this video. It's running a little bit long. Hope you enjoyed it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.